Welcome back. You know, some problems don't have just one perfect answer, but a whole bunch of them. Well, today we're cracking the code on a tool from math that's built for exactly that, linear inequalities. This isn't just about finding a single x. It's about drawing a map of a whole universe of possibilities. Okay, let's make this real for a second. Picture this. You're at the store. You've got exactly $7 in your pocket, and you're looking at the bulk bins. What mix of granola and muesli can you actually buy without that dreaded insufficient funds message popping up? I mean, there's not just one right answer, is there? You could buy a little of this, a lot of that, and that right there, that's the whole point. And this idea leads us to what I love to call the solution zone. We're not looking for a single point on a map. No, we're about to draw the entire territory of every single possible right answer. So what is this thing officially? It's a linear inequality. See, a regular equation, that gives you a nice clean line of answers. But an inequality, that gives you a whole shaded-in region. Think of it like a country on a map, where any spot inside its borders is a correct answer. It's a yes zone. Yeah, that's the big mindset shift here. We're moving away from thinking about the one right answer and starting to think about the entire area of possible answers. Any point inside our shaded zone is a combo that works. So how do we actually find this magical zone? Well, every territory needs a border, right? And in the world of inequalities, that border is what we call the boundary line. It's always our first step in drawing the map. Now, how you draw that line is super important. If your inequality is just greater than or less than, you use a dotted line. Think of it like an electric fence. You can get close, but the points on the line itself are not solutions. But if it's greater than or equal to or less than or equal to, you draw a solid line. That's a solid wall, and every single point on that wall is part of your solution. Okay, so you've got your border. The map is officially split in two. Now you just have to make a choice. Which side is the solution zone? Which side do we shade in? Luckily, the rule here is pretty intuitive. If your inequality has a greater than symbol, you shade the entire region above the line. Simple. If it's got a less than symbol, you shade everything below it. You do that, and boom, your shaded area is now officially your solution zone. All right, you're getting the hang of it. But I gotta warn you, there's one tricky little rule, one little trap that gets almost everybody at first. If you can master this, you're golden. Let's call it the flip. Okay, take a look at this problem here. Our mission, like always, is to get y all by itself on the left side so we can graph it. Looks pretty harmless, right? But trust me, there's a trap waiting inside. So the first couple of steps, that's just standard algebra. We simplify, we subtract 2x from both sides to start getting y alone. But look closely. We've got a negative y. To fix that, we have to multiply or divide by -1. And that right there is where the trap is sprung. This is it. This is the one rule you absolutely positively cannot forget. Anytime you multiply or divide the whole inequality by a negative number, that symbol in the middle has to do a complete 180. Less than becomes greater than. Greater than or equal to flips to less than or equal to. It's the most critical rule of the game. So after we multiply everything by -1, our original less than symbol does a backflip and becomes greater than. We're left with y is greater than 2x minus 3. And this is what we can actually graph. It's a dotted line with the shading above it. See how that one little flip changed everything? Okay, theory's great, but let's put it all together. Now that we've got the skills down, let's go back to a real-world problem and see if a specific situation lands inside our solution zone. So here we go, a classic fundraiser. The senior class is making $1.75 on every hamburger and $1.25 on every hot dog. Their big goal is to make a profit of at least $280. That phrase, at least, that's our secret code. It tells us we're using a greater than or equal to symbol. Now, let's say it was a pretty good night. They managed to sell 50 hamburgers and 100 hot dogs. So, the big question is, did they do it? Did they hit their goal? Did this point land inside the solution zone? To figure it out, we just have to plug and chug. We take the profit from 50 hamburgers and add it to the profit from 100 hot dogs. Is that total number greater than or equal to their $280 target? We run the numbers, and the total profit for the night comes out to $212.50, which, as you can see, is definitely not greater than or equal to their $280 goal. Bummer. So what does that mean in our inequality language? It means the point 5100 on our graph, it's outside the shaded area. It's not a winning combination. They needed to sell more of something to get across that boundary line and into the solution zone. And that's really the superpower of this whole thing. By drawing that boundary line, whether it's solid or dotted, and shading the correct side, while always watching out for that critical sign flip, you're not just finding one answer. You're creating a visual map of every single winning outcome possible. It's a roadmap to success. But look, this is way bigger than just math class. It's a whole way of thinking about goals and limitations. So think about it for a second. Your own life, your budget, your free time, your grade in a class. Where are your boundary lines? And what does it take for you to get into your solution zone?